Good morning, everyone. Welcome to my talk, The Code is Documentation Enough? I attempt to give a comprehensive overview of how to write expressive code that ideally doesn't need any comments to explain what's going on. I will also cover when a comment is needed and how a good one can look like. I understand this can be an opinionated topic, but I just want to show some best practices without being too dogmatic. Why do we want write expressive code in the first place? For guidance, we can look into the C++ core guidelines. The C++ core guidelines provide guidelines for writing so-called modern C++, that is C++ 11 and newer. The guidelines focus on safety, simplicity, and efficiency. They emphasize high-level issues like interfaces, resources, memory management, and concurrency, rather than style details. The rules are meant to guide architecture, be tool-supported, and gradually be introduced into the code base. There are also ongoing updates and community feedback. So let's look into one specific guideline. This is P1, express ideas directly in code. Reason: compilers don't read comments or design documents, and neither do many programmers consistently. What is expressed in code has defined semantics and can, in principle, be checked by compilers and other tools. We also get an example. In the first so this is a class that represents a date, and it has two functions. And here is how the core guidelines explain this example. The first declaration of month is explicit about returning a month and not modifying the state of the date object. Note that this first function is const. The second version leaves the reader guessing and opens more possibilities for uncaught bugs. The guideline is quite long, and there are two more examples that I'm not going to show here, but one is about using standard library features, and one is about using strong types. There are also more guidelines that fall into the category of expressive code. They are all in the philosophy section of the core guidelines. I won't go into details of the guidelines here, but I will touch on almost all of them during the talk. If you want to read the guidelines yourself, I've linked them in the slide deck here. But even if you don't follow the core guidelines, you most likely work in a team. You need to read other people's code, and they have to read yours. Or worse, you have to read your own code. And for that reason alone, it is a good idea to write expressive code. Because the longer you need to understand the code, the longer a bug fix or a new feature takes. And in the very worst case, no one understands what is going on in the current code base, and this can develop into a maintenance nightmare. We will look into different aspects of how to write expressive code. Starting with variables, functions, strong types, organizing code, unit tests, language features, and comments. And yes, comments are a part of this conversation. So let's start with variable names. Good variable names are sometimes obvious, sometimes not so much. Finding a good name for your variables makes the code easier to read and easier to change. So let's look at an example. This is a very well-known algorithm. Do you already know which one it is? This is a weighted average. But nothing in this function here is helpful to the reader. You don't even know which input is the values and which one is the weights. So let's change that. First, we give the inputs and the local variables proper names. Just by choosing descriptive names for the variables, the code gets more readable in an instance. It is way easier to reason about, and it's also easier to find potential bugs. Just to very quickly go over the algorithm, for the weighted average, the values need to be multiplied with their corresponding weights. The product of those values need to be summed up, and we also need the sum of all of the weights, and then the average, the weighted average is the sum of the product divided by the sum of the weights. Variable names can also be used to make parts of the code more readable. If you look at this code here, this is still a weighted average. But this time I used range algorithms and views instead of a raw loop. If you know the standard library, you know how to read this. A fold left with a std plus will sum up all the values in the given range. The zip transform will apply the given function to its input ranges. And even if you know how to read this, this can still be very hard to understand. In this case, giving the different stages of the algorithm names can help with readability. So now the different stages of the algorithms got designated names. The zip transform and the two-fold left got their own variable with a descriptive name. So even if you don't know how to read or use the standard library, you can understand what is going on in this function. It is not always obvious that a variable name might not be fitting very well. If we look at this example here, there are some issues. The zip transform pipeline got the name result, which somehow is correct, but it tells you nothing of what is behind this variable. So let's fix this. Let's rename result to a product of weights and values. Although quite long, this name tells you what the variable actually holds once it is evaluated. Now we look into the lambda of the transform view. The parameter of the lambda is called element, which is short for element, and we typically use this if we want or need to be generic. But in this case, we don't have to be generic. We know exactly what parameter we are dealing with. And it can even be misleading since LM is grammatically singular, but the parameter is actually a tuple of the values and weights. So therefore, the name should reflect this. A common pattern is to just name the variable after what is in the tuple. The right order here is also important. Value and weight reflects the values of the tuple. It would be very confusing if we would call it weights and values. You can avoid the naming issue here altogether by getting rid of the lambda and just use std multiplies, and it can even be simplified even further by using zip transform, as I showed in the examples before. So here are some best practices for variable names. Use words instead of abbreviations when possible. Sometimes it makes sense to use abbreviations if they are well known and understandable in the context of the function. See if the names are understandable in the current context. If you have a class called user, then it's totally okay to refer to the username just as name, as you are within the user context. Outside of the user context, there might exist more names, and then it is important to add the context to the name, for example, by calling it username. The name should also have no redundancies. User.username is redundant. It should just be user.name. The variable names should be consistent in language and style. It doesn't mean you cannot have different styles in your code. For example, variable and function names can all be snake case, while type names can be Pascal case. As long as you're consistent with it, you can mix these different styles. Prefer specific name over general ones. While data might be technically correct, it is too broad. Use a name that describes the data, like customer records. And try to be specific, but not overly so. Variable that holds the number of users in the database might be very descriptive, but it's also too long, and user count is enough here. So now we move on to functions. As already shown, if you want your code to be expressive. This also applies to functions. So we will look into some best practices of how to name functions. The same approach applies to the function names as to the variable names. But while the variable tells you what the variable holds, the function name tells you what the function does. It is related, but there are some differences. So let's look at this class. This is a very, very simplified model of a banking account. We create a new account by passing in the account holder's name. The account then holds the name, a balance, and a vector of transactions. Now we add some member functions. These functions are all called balance, but they all do something different. Can you figure out what these functions are doing without just by looking at this code, just by checking the parameters and the return types? Probably, maybe, yes, in this case, but in other cases, they might not be as clear. So functions So for functions, the naming should describe what the function actually does. The first function returns a balance, and if we return a member variable, we usually use get. The next function sets a new balance. Whether or not this is a good idea, it's not a part of this talk here, but if we want to set a value, we usually use set. And the last function updates the balance by adding a new transaction. So we should call this function update balance. Functions should have one clear purpose. If possible, try to avoid side effects. Functions should either return something or change something internally. Doing both at the same time can lead to confusing and surprise side effects, and it also makes the functions harder to name. So what about the valid function? It does not say what it is validating, so we should add that information to the function name. For functions that return bools, it is common to use verbs like is, has, or can. Also, function names should be short and to the point. Try to avoid overly long names like validate balance by summing up all the transactions to check if it matches the stored balance. That is a little bit too long, although very descriptive, but it makes the code hard to read. And if you have trouble finding a good name for your function, consider if your function maybe is doing too much at once. If that is the case, try to split the function into multiple functions and see if you can give the individual steps proper names. So here are some best practices of how to name functions. For function names, use verb and object to describe what the function is doing, like calculate user ID or get username. Functions that return bool typically have prefixes like is, has, can, or should. Side effects of the functions should be named, like update some member variable. You should also be consistent with the wording throughout the code base, like always use get if you want to return some member variable. And like with the variable names, be consistent with the language and the style. Keep it concise, like do calculate function is just calculate. And also, you can use domain language. Adjust price, total price by factor might be technically correct, but in the domain language, it is apply discount, and then it's also easier to understand. So we're moving on to strong types. C++ is a typed language, but it doesn't mean it is strongly typed. Just because the language is typed doesn't mean it is strongly typed. Then when we look at this function, to calculate the speed, everything is probably named. But if you look closely, you have no information about the units that are used here. Is distance in kilometer or feet? Is time in minutes or seconds? It might be the intention to make this a generic function to calculate the speed. But if it's not meant to be generic, then this can lead to hard-to-read code. And at the calling side, also, it can lead to errors. So on the calling side, it would look something like this. Here again, you have no information about the units. So we can add a little bit more information by renaming speed into speed in meter per second. Now the result got at least a descriptive name, which is a tiny bit better, but also, not really enough, because there are other issues here. You still don't know the units of the distance and the time. And even worse, you can switch the arguments, and it will compile totally fine. It will not tell you anything about any errors. So to prevent errors like this, we have several options that also increase readability. So the first option is to encapsulate the inputs into a struct. You typically do this when you have lots of inputs or multiple inputs of the same data type. Like imagine 10 inputs, all of the same data type. This can get confusing quite fast and lead to errors when you get the order of the arguments wrong. You can then use structured bindings if you want to deconstruct the struct in the function if it increases readability. So what do you gain by using a struct? You can now use designated initializers when calling the function. Now you can see clearly on the calling side which parameter is the distance and which is the time. It makes it easier to read and harder to get wrong. This is one way of making the parameters more obvious and easier to use. But there are other ways of achieving this. So let's walk away from using a struct for a bit. Let's say we don't want a generic function. We need the inputs in certain units. For instance, the distance we need in meters and the time we need in seconds. So speed is meters per second. When you want to improve readability of functions, you can use type defs for this. In this case, all of the underlying types are double. So now we have named types that we can use in our function. When calling this function, we didn't improve anything at the first glance. Although it is not needed to compile, you can now add the type defs to your function call. We now made a significant improvement on readability on the calling side. While this is a super lightweight solution, it has one major downside. These type defs are just aliases. They are not their own type. So that means I can write this, and it will compile without any issues. So while aliases are lightweight, they improve readability, they are not type safe. But we do have some type safe options. We can define a type safe type ourselves by using a struct. The struct then is the strong type. We do that for all the types that we want to use. Here it is meters, second, and meters per second. Now the function can use these structs as inputs and outputs, and you will have to provide an instance for that struct to make it compile. That means it is no longer possible to switch the parameters around like we saw with the alias version. But it comes with its own challenges. You might be asking how the compiler knows what to do with this division here. And of course, like always, there are many different ways of implementing the same thing. In this case, we could call the dot value for distance and time to make use of the built-in division operator for doubles. This is one way of implementing the division here, but we can also provide another function to perform the division or overload the division operator. This is what I did here. By overloading the operator, the usage becomes natural and readable. But only if the overloaded operator doesn't contain any surprising implementation. So you have to be very careful with that. This can look like a huge downside, as you have to provide a lot more code to do the same thing as with the built-in types. But it is also exactly what we want in some cases. Imagine the unit case here. It doesn't make sense to add a time to a distance. And this can lead to errors. So by using strong types, we can prevent that from happening during compile time. Other operators do make sense, like this division here, and therefore we can provide specialized code for it. You can define what is allowed with your type and what is not, and that is also a strength of the strong types. Now I think a lot of people are already screaming in their heads, use a units library. And of course, they're right. There are different units libraries that you can use, and I'm going to use MP units by Mateusz Pusch. The advantages of a units library is that all of the units are supported without you having to define your own thing. And all of the operators are taken care of, and what is also very important with physical units, the conversion between the units is also taken care of. So this example now uses MP units, and you don't have to define the result type, but if you want to give it a name, you can. Otherwise, the result type will be like a huge templated type. But if you never need the result type for anything, you can just use auto and not deal with it. When calling the function, we can create the correct types by using the unit symbols. So using strong types does not only make your code safer, but also more expressive. While physical units are a perfect use case for strong types, there are more. They are used when security is a concern or when there are several parameters that have the same underlying type. I showed you a simple way of defining your own strong types, but you don't have to reinvent the wheel here. There are many handy libraries that you can use for this. Some of them are on the slide here. And I guess there are even more libraries that deal with this kind of thing. And there are at least 3 specialized libraries for physical units, and I highly recommend to use one of them if you're dealing with physical units. So to summarize, strong types have a lot of benefits. They prevent mixing up parameters when used instead of plain old data types. And there are checks that run at compile time, which is the place where we want to catch the errors early. The interfaces become more readable as you not just see from the names, but also from the types what the function is doing. The types themselves also can have built-in checks. For example, a percentage type could check in its constructor that the value is between 0 and 100. There are less implicit conversions in functions, so built-in types can silently convert into other types, which can lead to bugs. And also there are lots of libraries that you can use that support you in defining your own strong types. And again, I particularly recommend to use a units library when you have to deal with physical units. And Mateusz Pusch also has a great series of lightning talks highlighting various bugs that were caused by unit errors. So now we have talked a lot about how to name things. But one other thing that is important when trying to write readable code is how the code is organized. In general, we want to avoid spaghetti code. That is code where a lot or even everything is done in one large function. It is very hard to read and also very hard to debug, especially when variables are initialized all over the function and then changed throughout. This is very hard to track, and it can also be very bug-prone. So just consider this code. It is just calculating some statistics. So first, finding a good name for this function is not easy because this function is doing so much at once. So it is advised to refactor this and move the individual calculations into their own functions. Sometimes you can find a particular pattern in the code, which is a comment describing what the following code does. So we can use this pattern to divide the function into smaller individual functions, as the comments not only indicate where a new algorithm starts, but it already gives it a name. So now we have dedicated functions to calculate the different statistics. This has many advantages like improved readability, reusability of these functions, and now they can also be used somewhere else in the code when needed. They are also now better testable because you can test them individually, and with small functions you can oversee changes more easily and therefore enable safer code changes. There are lots and lots of coding guidelines when it comes to how to write code. They might be seen as irksome, but they're meant to improve readability, testability, and also reduce bugs. One common guideline is to restrict the number of lines a function can have. There are a lot of different guidelines regarding the number of lines a function could have. Some say up to 100 is fine, others say more than 5 already needs refactoring. I see these as extremes of a spectrum, so I personally think like around 20 lines is fine. And with the above refactoring, we reach that goal. And a line limit can be like a hard rule that is enforced, or it can be a guideline. When moving code to their own functions, you should also keep in mind that you should keep one layer of abstraction. If you look at this code here, you see that these 2 functions describe what they are doing. They are calculating the mean and they are calculating the standard deviation. So this is one abstraction. And the calculation of the variance describes how it is calculated. So this is another layer of abstraction. Mixing these layers can lead to less readability. And what we should do is to move the calculation of the variance into its own function. Now we're keeping one level of abstraction in the function, which is more readable. And as I said before, now the variance function can be used elsewhere in the code, and it can be also tested individually. Another common guideline is to restrict the number of parameters a function can have. So this is to prevent the function from doing too much at once. It is common to view more than 3 or 4 parameters already as a code smell. So if you consider this function here, which takes 4 doubles to represent 2 points. For readability reasons and also to reduce the number of parameters, we could define a struct called point to encapsulate the coordinates. This is a very common strategy when dealing with lots of inputs or large parameter sets. And it also bundles together parameters that belong together. For functions that use booleans as input, or a lot of booleans as input, it is advised to use enums instead. So as you can see directly here, in the first line, you have no idea which settings were set when calling the function. And in the second line, you know exactly which settings were used. And you should also avoid too deeply nested scopes. Coding guidelines typically say not to have more than 2 or 3 nested scopes. And this is because the code is very hard to read when it contains a lot of brackets and indentations. You can quickly lose the overview of the functions, and bugs are more likely, for example, being in the wrong else block or adding a break at the wrong position. So to avoid this, consider early returns. You can test the conditions of the parameters at the beginning of the functions and then react accordingly. All of these best practices aim to improve readability and also therefore reduce bugs. So some teams set a line limit for their function, and as I said, there's a lot of debate around the maximum lines a function should have. I think a reasonable line limit can keep the scope of the function small. Most coding guidelines say to not use more than 3 parameters in a function. Using more can be an indicator that the function is doing too much at once. You can always encapsulate parameters in a struct if needed. The depth of nested scopes should not be more than 2 or 3 layers, and you should consider using early returns. You should also keep one level of abstraction to improve readability and also testability. And I didn't show them here, but they are refactoring tools and tools that enforce coding guidelines that you can use to support you here. There are way more coding guidelines that I can show in this talk here. And if you need any guidance or inspiration, you can Google guidelines of big companies, as they can be typically found online. So we're moving on to the topic of unit tests. I hope I don't need to convince you that unit tests are a good idea for numerous reasons. One reason is that it also is documentation of how the code is used and which edge cases and boundaries exist. For the why and how to unit test, I'd like to refer you to Kevlin Henney. He talks a lot about testing and programming with guts, that is good unit tests, is one talk that I remember quite well. And he also gave a workshop exactly about this at this conference. Unit tests allow you to find errors early, enable safe code changes and refactoring by checking regressions, improve trust in the code, and also document the behavior of the code. So now that we're all on board with writing unit tests, let's see how we can write one that documents what the function is doing. It doesn't matter which testing framework you're using, it only matters that you're using one. So test functions need to explain what they are testing. So when you read the code and also when the test fails, it should tell you exactly what is going on and why it failed. There are different naming patterns for unit tests. So let's say we want to test that the mean function throws an exception when the input is empty. So I looked up some common patterns for how to name tests. And one pattern is method name, state under test, expected behavior. That would be a calculate mean, empty input throws exception. Another common pattern is given when then. given empty input when calculating mean, then throws exception. Should expected behavior when state is another common pattern, like should throw exception when input is empty. And you could also use just a descriptive sentence, which is often what is used in Python, like test calculate mean throws exception for empty input. So this is probably what I typically use in my own unit tests, because it just feels a little bit more natural and it reads a little bit more natural. If you want to use a naming pattern or not, that is up to your team. If you use a naming pattern, it can help with consistency in the tests. And so you can spot easily what is going on in the test. But it sometimes is hard to stick to a certain pattern for all of the unit tests. I also want to emphasize that it doesn't matter if you use one of these patterns or not. The most important thing is that the test name is clear and you and other people know exactly what the test is testing. So let's go back to testing the mean function. A first test case would be that the mean can be calculated when the input is not empty. So let's start with that. A good unit test is testing one thing at a time. It also tells you what is expected from the function with a given input. So just by looking at the unit test, you can see what a function or class does and how to use it and what the corner cases are. For calculating the mean, we should also consider what the function does when the input is empty. It could throw an exception, return an error code, or just even return 0. And what is implemented here can be determined by good unit tests. So if someone changes the behavior of the function now, the unit test will also detect it. So writing good unit tests is good practice in any case, and if they are well written, they can tell the reader a lot about the implementation of the function or class and how it is supposed to be used. It's like a built-in manual for your code. So we're moving on. Language features also help with safety, and they can also help a lot with readability. So first I would say you should know your standard library. I know standard library is not a language feature, but it is part of the language. And a C++ developer should know their C++ standard library. And the same goes with all of the other languages. The standard library is tested and stable, and of course it can contain certain bugs, like every other software can, but it's far more likely that you introduce bugs when you implement your own functions. So using the standard library also means that you don't have to write and maintain this code yourself. The standard library features are also aimed to make the code more readable. It provides a familiar and consistent solutions, and developers don't need to understand custom implementations. They can look at the standard library and immediately understand patterns and meaning, and this makes the code easier to read, maintain, and share across the teams. So I can only highlight a few standard library features and language features in this talk here. So you might have noticed that I used const throughout of my code examples. And that is on purpose, because using const everywhere when possible is advised, and it also tells you a lot about the code. Const parameters will not change in the function. In fact, it would be a code smell if they were not const. Same for local variables. I would instantly recognize if one of these variables would be non-const, and I would wonder why. Why would they even change throughout of the calculation? So I know it's not necessary, but I also use const in the header files for documentation reasons. So we should aim to write pure functions. That is, functions that have constant input and return a value without having any side effects. But sometimes we cannot avoid an out parameter. For example, to prevent a copy from a non-movable data structure. In this case, a non-const reference of a parameter conveys the information that we are dealing with an out parameter. So this is why you should be consistent with the usage of const. When you're consistent, it reduces the mental overhead of tracking the changes of the variables and trying to figure out the interface. And so you know exactly which is input, which is output. I am personally also a huge fan of concepts. And with concepts, you can perform compile time validations of template parameters. This not just makes the code safer, but also more readable. You can now see directly in the interface which types are supported by the function. Concepts also made the code way more readable, especially compared to enable if. On this slide, you see 3 ways of using the range concept random access range. And the first style you typically use when you want to perform more complex validations, like checking if the range is random access and maybe the value type is floating point. The second style is typically used when you want to apply one check, but you also need the template type in the function. And the third is typically used when you want to apply one check, but you don't need the template parameter anymore in the function. But you can use them however you want to. So in my opinion, this clearly is an improvement on readability and also safety. And if you have constraints on your template parameters, please use concepts to check them. And also a lot of functions have pre and post conditions. Currently, they are most likely be ensured by if clauses, asserts, or macros in the implementation of the function. Preconditions are most likely tested at the beginning of the functions. Therefore, by looking into the functions themselves, you can most likely see these preconditions up front. And post-conditions might be checked at the end of the function, but more likely that they are checked at the calling side so that you got the correct result. Currently, most code probably uses if statements like this, but there are also libraries that you can use, like the guideline support library, which provides expects and ensures macros, which implement contract-like features, and the program will by default terminate if the pre or post conditions are violated. And with C++ 26, we will get contract support. And they will probably look something like this. And one big advantage of contracts over the previous implementation is that contracts can be put into the header file. And therefore, humans, compilers, IDEs, static analysis tools can read them without having to access the implementation. So again, this improves readability and also safety. I am far from being an expert on contracts, but Timo Dumler is. So I recommend to check out his talk about contracts, like this one he gave this year at ACCU. So to summarize some of the advantages language features and standard library has. A standard library is part of the language, and software developers should know their standard library. The standard library provides tested and efficient functionality. It saves you time and support if you use it instead of implementing your own version of it. What I didn't mention here are features like the algorithm library, numeric library, ranges, chrono, and so on. And all of them, if you use them, can greatly improve readability of the code. There are only a few instances where const is not advised, like if you have a class and they have member variables, and if you make them const, they cannot be moved anymore when the class is moved. This can be okay for like built-in types that they are copied around, but maybe you have like a big data structure that you're storing within your class and you don't want it to be copied, you want it to be moved, then it has to be non-const. It's just the only thing, I guess, where const is not advised. Otherwise, use it wherever you can, make const whatever you can make const. Concepts are used for compile time checks for template parameters. It makes clear which types are supported by the function, and it greatly improves readability, especially compared to enable if. And we will also get contract support with C++ 26, so it can use to check pre- and post conditions of functions at runtime. So I'm very sorry if I didn't mention your favorite language feature here or your favorite library feature, but I only have so much time. So what if you used all of these techniques, all of the best practices, but your code still needs some more documentation? Well, then you should write a comment, right? In general, a comment should not describe what the code does, but why it is there, why it is needed. So here are some examples of what can be considered a bad comment. So in the first example, we have some redundant documentation. You can see clearly what is going on in the function, and it does not need to be explained any further. In the second example, the comment is outdated. At some point, the code was changed from using the mean to using a median, and no one ever changed the comment. In the next example, we have a to-do in the code. In my team, we have a rule to not leave any to-dos in the code. We should fix it right away, if possible, and if it cannot be fixed, then we should explain why the code is there, and then add a corresponding issue in our issues tracker, so it is possible to find this again and come back to it and fix it. Otherwise, this will be forgotten. No one will ever come back to fix these to-dos. And jokes and insider comments might be fun, but they don't add any value to the code, and it can also be very confusing. But there are some places where a comment is needed and where it's actually valuable. So in the first example, the comment explains why stable sort is used instead of another sorting algorithm. Without the comment, it might not be obvious why this is needed, and it may be changed accidentally. Next, there's a comment that documents a workaround of a bug. This is also important to document, so you have the chance to come back to this code to fix it once the bug in the compiler has been fixed, or in the library. This also needs a corresponding issue in your issues tracker. That's very important. And some internal logic might not be super obvious, so then a comment can help to make it more obvious. So again, this is a why comment, so why this code is there. And if you're using static analysis tools, they sometimes get it wrong. And then you want to disable warnings for issues. Typically, you want to additionally describe why you are disabling this current warning or issue. And also, not every code is easy to understand. You have sometimes very complex calculations, like very complex mathematical things going on. And here, explaining what the function or what the mathematics behind it is doing, or linked to an external documentation is very helpful in understanding the code. So I took this from Python SciPy library, and I have no idea what a Henkel matrix is. Sometimes we also specialize code. So we take some generic code, maybe from some library, and we specialize it to only support one use case that we have in our code. Then it is also helpful to explain where this code is coming from and how and why it was adapted and specialized to the use case. And lastly, external APIs are often documented extensively. And again, I took this from Python, this time from the NumPy library. As you can see, I'm not for not ever using comments. But if you use them, make them good, correct, and useful. And also, if you change the code that has a comment, read the comment and see if it needs any updates. Now, lastly, how can you ensure that the code is actually readable and adheres to the coding guidelines? There are tools that check coding guidelines like ClangTidy, ReSharper C++, or SonarQube. Other tools ensure that the code has the same formatting throughout, like Clang format. Consistency improves readability. But there are no tools that I know of that check if the code is actually readable. This is still a human task. And code reviews are a good place to do this when there are different ways of doing code reviews. So what we do in our team typically is that we review the code ourselves without having the author telling us what is in the code. Because if you cannot understand the code someone else wrote, then this is an indicator that something needs to be changed in the code, or that something needs a comment. And if someone explains the code to you, you typically understand it. So try, when you're doing code reviews, try at the first time just to read the code by yourself and see if you can understand it. Also, a very useful tool is pair programming. Talking to someone else and discussing how to implement something can also greatly improve readability and then make the result more easily understandable. But I still would want to get a review from someone outside of the pair. So, to summarize, giving your variables and functions clear names that are descriptive but not overly long will tell the reader what is going on in the code. Using strong types are a good idea for many reasons, but they also document the code even further by including concrete information on the use types. By bringing the code into a good structure, you can also improve readability, and tools can help enforce coding guidelines if you have them. Unit tests are best practice anyways, and they also document the code and how it's supposed to be used. So for unit tests to function as documentation, they need to be clear descriptions of what they are testing. And also all the paths need to be tested, not just a happy path. Using language features like concepts, contracts, or even const, you can express the intent of the code. And sometimes a comment is useful. I showed some examples for that. And you should use common sense when to determine how and when to write a comment. I personally don't believe in extremes, so not everything needs a comment, but sometimes a comment can be really useful. And lastly, these things can hardly be enforced. There are no tools for checking readability. There are some tools for checking code guidelines and applying formatting. So you still need a human in the loop to determine if the code is actually readable or not. And doing code review is a good time for that. And lastly, be consistent, but maybe not be too dogmatic about this. Common sense, I think, applies to all of these rules and guidelines. Thank you. Yeah. So the question is, sometimes you need external documentation, like external documents, and where to draw the line between where you document in the code and where you use the documentation, right? So I see this as two different things. So the comments in the code are used for the developers. So they are meant for you as a developer to help you understand what is going on in the code. External documentation is for external people, mostly, or new people maybe in your team. So this is a different kind of documentation. You need to be more extensive, and you maybe sometimes you need to be more high level, just to explain what the scope is or what is implemented. And in the code itself, you are, I guess, way more low level and explain what is going on in the different functions. So yeah, that's, I guess, where I would draw the line. So one is a little bit more high level, so that also external people can understand it, and one is for the developers, so that the developers can understand what's going on. Okay, if there are not any more questions, then thank you for coming and have a nice day.